something else. So anyway, so the last couple of days we talked about structure-based models and general ways in which they can be used and sort of the strategy behind them. We also yesterday went over a basic introduction to just how do you get your calculations up and running. And today I'll give some tips for how to use these models effectively for larger systems. So what's nice, one nice thing about these models is they're less expensive, so you can explore ideas for very large systems without a tremendous overhead. However, these large assemblies can very quickly have hundreds of thousands of atoms or millions of atoms with cryo-EM improving rapidly. We're constantly getting these enormous assemblies that you might want to look at. And so, I'm going to give some tips of how to maybe reduce that overhead, because even though these are considered to be very inexpensive models, you could still run calculations on thousands of cores simultaneously for a single trajectory. So they get big. But that's not really practical for most people. As before, you can download the presentation. There's a PDF in the workshop directory on the Smog server. There's also some supporting files available for the exercise aspect of this session. So we'll spend about half the time talking about the ideas behind some strategies, and then we'll also go through a little example where you'll use a new tool we've developed to try to make your calculations a little less expensive. So as I said, we're going to discuss some performance considerations and computational load considerations. This is not extremely technical, but it is a little bit, so it doesn't go into normal research talk. This is really, if you would like to start messing around, these are some things to know. And in addition, it's not really specific to structure-based models. We're using them as an example, but all these ideas could be applied to other other models that are out there as well. You could, in principle, use all of these techniques for explicit solvent simulations if you wanted to, but we're going to show, in our case, how we've used it with the simplified models. So for a little bit of motivation, this is the ribosome, which I was telling you about when I started looking at the ribosome about 10 years ago. Everyone thought it was a bit outrageous that we would apply these models to something this large. And that was pretty much the biggest thing that had a full atomic structure available. Now you have things like the HIV-1 capsid, and this is pretty much drawn to scale, where each bead that I'm showing, this is not a coarse-grained model, it's just a coarse-grained drawing. Each bead is a domain of a protein. So this is actually roughly 1,600 proteins assembled into this big shell for about 2 million atoms. And last year we actually did simulate this using structure-based models as sort of a test of the new software to make sure it actually works well. So if you want to start looking at these big systems, you could try to use explicit solvent simulations, which people do, and you'd run 100,000 cores and you'd look at a microsecond of time, and you can say some interesting things about the system. But if you want to look at really large-scale motions, global fluctuations of the shell, that's not really a practical way to go, so you might want to look at these simpler models. Now that being said, not every question requires the entire system to be simulated, so you could just look at the whole system for part of a trajectory, and then part of the system for the rest of the trajectory, because maybe there's a global conformational change followed by a more local conformational change, in which case you don't want to be simulating 2 million atoms for months when you're really just looking at 50 residues and how they move in this last step. That's going to be quite a waste of resources. So can we have some strategies to reduce this load and just simulate part of a system without giving us problems with our results? So as some motivation, I showed this this trajectory in my talk 2 days ago, where we were looking at the ribosome, and we said, okay, everything sort of moves a little bit, and there's only one thing that moves a lot, and that was this tRNA molecule. This tRNA was undergoing this 100 angstrom conformational change, and what we learned, or we sort of suspected anyway, was that the fluctuations in the ribosome are actually quite important for the dynamics of the tRNA molecule. So if all these helices were just rigid pieces, you would get a completely different answer from when you consider the actual flexibility of the assembly. That being said, these aren't global rearrangements, these are all local rearrangements. So it's not that the subunits are moving relative to one another. So in principle, you could just simulate part of the system, just say the atoms that are sort of in the vicinity of this tRNA molecule. And so that's what we were looking at a couple of years ago. And so we started playing around with ways to do that in a more rigorous fashion. So I presented the results of what we got with these models. Now I'm just going to tell you what we actually did in the and what I wasn't telling you about a couple days ago. So if this is the whole ribosome, for most of the studies that we've been doing recently, we only wanted to look at the region near the tRNA. So instead of looking at 150,000 atoms, we could reduce it down to about 24,000 atoms, which is a nice reduction, factor of 8 in your computational load. When you combine that with the fact that cores are getting much faster and nodes are getting much more powerful, when you go from this system size down to the smaller system size and use a modern node, on one node you can get 5 to 10 times the sampling per day with this system than we were able to get for the entire system with 8 to 16 nodes just a few years ago. So we're really at a place where what I was showing you before, these big changes, we were waiting for 3 weeks on 128 cores. If you were to repeat it now, you could actually do more in 2 days than what we were doing in 5, 6 years ago. So we want to reduce this load, and to do this, we need to be very careful about how we treat our boundaries. If you look at the literature and you look at people who are studying large assemblies, but they're looking at small changes, they almost always do this. They pull part of the system out, and then they put restraints on all of the boundary atoms. And there's really never much of a discussion as to how these boundary restraints are imposed. And so if you, in our case, look at this boundary and you just color it by the RMSF observed in the full ribosome, some things don't fluctuate very much. It's less than an angstrom. Other regions are 5 or more angstroms. So it's very heterogeneous what is happening at this boundary. So just looking at the RMSFs, you can already say, well, if you just put in some constant restraint on each atom with the same value, who knows what type of perturbative effect that could have on your overall system, and then that could propagate into changes in your actual tRNA motion. And that's not very desirable if every answer you get depends on this arbitrary decision of what you included and how strong that boundary restraint was, right? I mean, you might still be able to get published, but I would be very nervous that everything I'm saying doesn't mean anything because I misrepresented the boundary, right? We wouldn't solve PDEs without boundary conditions, right? Or just arbitrary boundary conditions. We need to know something about them. So if we look at this case, this is just the RMSF of we identified as being at the boundary of this example. So there are about almost 4,000 atoms on the boundary out of 24,000 atoms in our system. And I'll define what I mean by a boundary atom in a bit, but about a seventh of the simulation is actually composed of atoms that could have an artificial boundary effect if you weren't careful. And if you look at these fluctuations, these are the scale of fluctuations in the full ribosome. Again, it's very heterogeneous. And I've artificially capped it here for this example at 5 angstroms, just for some technical reasons. But these peaks actually would go up more to around 9 or 10. So you get this very, very wide range of types of motions that you're going to see at this boundary. So what I'll tell you about is how we addressed this type of so that we could not introduce artificial effects. So the first thing you have to do is define what you're calling boundary atoms. What we say is when we delete everything outside of the box, we have cut bonds through the middle. So you have atoms that have bonds missing. You have atoms that have bond angles missing, dihedrals missing, contacts missing. Anything that had something removed, we can a boundary atom. And we say that is a candidate for something that we need to do something to, right? We need to account for the fact that we have just introduced this perturbation in its native interactions. So that's how we get this list of about 3,900 atoms. It's just things that had interactions removed. Okay. Then, as I showed you, we calculate our RMSF for those boundary atoms, but in our full system. Okay. So a full ribosome simulation, doing it once with a structure-based model, again, you could do it on your desktop in a day or two probably, and you could get all these RMSF values for a pretty large system. So you get your RMSF values, and this is what we would like to be happening at our boundary. We pull out this truncated system, but we want the boundary to behave in this manner. That's the goal. So what we do, and I did this in collaboration with Vitor and Jeff and George as well, we said, well, let's start by just putting in a harmonic restraint on every atom positioned at the position of that atom in the original model. And we picked some arbitrary value of this K value. I can't remember what we used exactly, but we set it to something that was on the order of KT per angstrom squared. So when you do this, here's our what we would like, here's what we get. Okay, so it just doesn't look at all like the fluctuations you would expect in this box, and that's not surprising because, as I said, this is an arbitrary value. Right? But at this point, I would be very concerned that nothing in the simulation will mean anything because the boundary is just completely wrong. Right? So what do? Is we take these this run and we calculate these RMSF values, and then we calculate the average mean squared fluctuations from that truncated system, and then we compare that to the average mean squared fluctuations in our full system for these boundary atoms. And then we simply rescale this K, every K by the same factor. So it's sort of like a steepest descent to minimization in a sense. And so if we rescale this and our fluctuations are too small, that means our Ks will be reduced, so the fluctuations should then increase. So we do this, and then we have a new K value. We repeat our simulation. We recalculate our fluctuations. We compare them again to the target and update again and again and again. And we just keep doing it until this ratio is very close to 1. Okay? This works pretty quickly. To get the average fluctuations correct, we only did 5 iterations. And if black was the original fluctuations, red are the new fluctuations. And while it did bring down the average, everything came down, you can still see these red spikes are pretty much everywhere. So there's pretty much no correlation between what we would like and what we have at this point. So even if you put the right scale of the restraint, you could still be introducing tremendous boundary effects that are not desirable. So then the next step is, rather than updating all the K values by the same factor, we look atom by atom. After those first 5 rounds, we do the same thing. We perform our simulation. We calculate the mean squared fluctuation of atom I in this truncated system. We have the mean squared fluctuations in the full ribosome for that same atom. And this 1/2 is just sort of a damping term in how we rescale things. So the same idea is true. If our fluctuations are too small, this will be a smaller value, and the Ks will be reduced. If the fluctuations are too large, this factor will be greater than 1, and the Ks will be increased to bring down those fluctuations. So we do this at each step, and we update all of the K values, but now they're done heterogeneously. So every atom's restraints are getting tuned to try to match these boundary conditions. So we go through, and after 34 iterations, here's what we get in this case. So black was the target, and red is what we get in our truncated system. So now we have a system that is 1/7 the size of our original system. The boundary, though, is behaving with the scale of the fluctuations basically exactly how we would expect them to be based on the full system. So even though we've pulled out 130,000 atoms from our simulation, the boundary is still behaving in the same way, at least at this scale of the motion description. I'll just say as a cursory note, we also have anisotropic harmonic restraint tools implemented where we just put direction as well. But we're not talking about those details today. And this figure is something that you should not forget when you're looking and reading papers or seeing people present these truncated systems, because these are the strengths of the restraints that we get after this fluctuation matching tool is applied. And the strengths vary by 4 orders of magnitude depending on which atom you're looking at. So if you just take one value, you can expect the answer to, let's just say it's not always right. Okay, there might be cases where it's not so dramatic, but you should definitely be cautious. Okay, so you can set this up, and now we have all of our boundary atoms restrained with unique strengths. And if you watch the simulation of just the box, you see this boundary is fluctuating around. You can't tell whether you just pulled it out of a full ribosome or you simulated it by itself. And so this is an effective strategy for not simulating these enormous systems for long periods of time. If you have a local conformational change, a local meaning still 50 to 100 angstroms in this case, you can save a lot of computing power and a lot of disk space and a lot of effort by adopting a strategy like that. Now today, well, for those of you who have the Smog 2 installed, we'll go through an example of how you would start to do. So we have a few tools available. We're not going to go through and actually refine a whole system because each iteration actually does take about 3 hours. So that 34 iterations took about a week to run for this case. So we're just going to set up a truncated system so you can get an idea of how you would take a structure and then prepare a truncated system, which you could then apply this iterative tool to. Okay, so for those of you who are going to follow along with the steps, we're going to look at the all-atom structure-based model of the Chaperonin system, the same thing we did yesterday. Again, the connection's a little not so great right now, so I would suggest just downloading the prepared force field. If you want to load it, just upload it, give it a name, and hit go. All the default values are being used, so there's actually nothing special at the step of generating the force field. It's just the standard all-atom structure-based model. So you download this tarball, unzip it, untar it. You will have all of the files that you would have generated had you loaded it to the page. If you are using Smog 2 locally right now, you can do the same thing we did yesterday, but just say -AA instead of -CA, and you will get the all-atom model. Okay. So in this system, you have about 60,000 atoms, and you could imagine that you want to look at a protein interaction in some region, and you don't really care what's happening in the other half of this assembly. So we would just want to say cut a piece of the system out and study that piece of the system, and we would want to put in some restraints on the boundary atoms of this truncated system. So the way you would do this is typically you go into VMD and you figure out what you want to pull out. Okay. Now I'm just showing a few tips for those of you who are not that familiar with VMD. VMD is an incredibly powerful program that most people don't realize how much it can do. But you can just select atoms based on coordinates. You can pick them based on names, residue names, indices, whatever you want. You should really read up on all of the options for how you can make these selections. In this case, if you put selection z greater than 130 and x greater than 100, just saying the z coordinate is greater than 130 angstroms, x coordinate is greater than 100 angstroms. So if you have your system, you can start to sort of figure out what region it is that you want to look at. In this case, I just picked these somewhat arbitrary numbers just for demonstrative purposes of trying to pull out part of the system. So you can go ahead and do this and make sure it looks like this. If you're using the right PDB structure that I provided, that's what it should look like for you. I'll give you guys a minute to get that. And you can follow along if you would like. It loaded the wrong file. It changed the position, yep. I had the right, I was using a pre-processed file, so it was. What is going on? Well, that's okay, well, the PDB file is on the page here. I'm sorry, did I must have. No, something went wrong in what I prepared. Well, my apologies for that. I must have copied the wrong number down. Okay, so let's change the values and just say z greater than 50. Those numbers I picked apparently were for a structure that was aligned somewhat differently. For this exercise, it's really not important what you pick as long as you pick something. So in this case, we're just saying z greater than 50, and it gives us this upper region of the chaperonin. And now, so you go through, you pick what you'd like to keep. Something that a lot of people don't realize when they first start using the VMD is this, what's called the TK console. This is a very powerful text-based interface that you just go to your extensions, TK console, and you can start using commands to do many manipulations. So what we're going to do is, since we've already selected what we would like to include in our simulation, we'd like some way to pull out those atom numbers. We just want a list of atom numbers. So we can say, let's pull those out from our model. So if you look in the presentation, you go to the TK console. And what we're going to do is we're going to define a selection of atoms. And this is now going to be z greater than 50. So we set this value, we'll call it top. And we'll use the atom select option, molecule 0, corresponding to this ID right there. And then we say what our atom selection is. So we'll say greater than 50. So all we've done is we've defined a variable that contains all of the information about all of the atoms with z greater than 50. And you can then go and check how many atoms are in that selection. And in this selection, we say $top because top is a variable. What is the number? It's 8,928. So we've pulled out a list of 8,928 atoms. And so in particular, a lot of graduate students will try to make their own scripts to do analysis, and this TK console is very powerful. So before spending a lot of time making elaborate manipulations, Google and look for these things, because the tips are out there. And this is much faster than having to write a script that reads a PDB file, checks the coordinates, and then saves the list of atoms, right? You just used directly a VMD selection command to select that group. We could also put, instead of z greater than 50, we could say name CA. If you wanted to just pull all the C alpha atoms, or you wanted to pull C alpha atoms and z greater than something, you can put in all the conditions just as you would in the representation window. Then we just want to open an output file that we are going to write that list to. And you can just copy that, set output file to this new file we'll call subset.include. And then we will write the list to that file. So this is just saying, put this information in this file. Top is our variable, defining our group of atoms. And for that group of atoms, we're going to get the serial, the indices, essentially, except instead of counting from 0, it's going to count from 1. So it's just going to write the list of atom numbers from that selection that we just picked. And then we'll close the file. And if you look in your working directory, you'll see a file called subset include. Okay? So we've made this file that now just lists the index of all of the atoms in that selection, in this case, Z greater than 50. Okay? So from a technical standpoint, it's actually very quick when you consider we didn't have to make a PDB parser, we didn't have to format anything, we just said, get these numbers and save them. Then, all we've done is we've defined our subsystem. Now what we would like to do is take that list of atoms and tell the Smog tools to pull all of those atoms out from our original model, pull all the energetic terms associated with those atoms, re-index all the interactions so that we only have those atoms in our new system, and make everything sequentially numbered so that GROMX can still perform a simulation. What we would also like to do is we would like to say anything that was a boundary atom, something that had an interaction removed, introduce a position restraint on that atom, because otherwise things will just start flying apart. So this tool that we've made that's part of Smog 2, it's only in the beta version of Smog 2. So if you download it Smog 2 and it wasn't the beta version, then this tool will not be visible. So my apologies. I can give you the prepared subset.top and grow are actually in the workshop directory in case you don't have the right version of Smog 2 to run this command. So all it does, we've tried to make this as easy as possible and completely compatible with all of the structure-based models, is you call Smog Extract. That's the module. You tell it what is the topology file, defining your force field, what is the coordinate file that you have associated with that. Give it a file that just lists all the atoms, and this could be delimit it or new lines or tabs. It will parse it, but it's going to read every atom, every index listed in that file and say keep it. Okay. If you have redundant numbering in this file, it will complain. So it's not the smartest script, but it's okay. It will catch a few obvious mistakes that people can make. And then you have to tell it to write out the new topology file, write out the new grow file, and tell it to include restraints on all of those atoms that had interactions removed. And we're going to put them at a strength of 1,000 units of energy per nanometer squared. That's the default unit that is used in GROMX. And that information will be stored in our new topology file. Okay? So, if all works well, then we Smog Extract, say our topology file, our grow file, what's the list of atoms, what is the output, and include restraints. It also will not overwrite your files. So we've tried to make it protect you from yourself or protect us from ourselves. Run the command. It's reading your topology file, it's reading your grow file, reading your list of atoms, and it's now generating a new topology file and a new grow file. And if you get this nice message at the end, success, it will tell you how many atoms are in your new system, and you have now defined a subsystem, which is literally just a cutout of the original system. Okay, so the reason for doing this, as opposed to just taking your cutout and then trying to apply it through the Smog tools, is that in some of these models, the distribution of energy depends on how many atoms there are, and there are a lot of counting rules for how you assign, say, the strength of a dihedral or a strength of a contact. So if you just take some of your atoms and run it through Smog, those numbers may not come out to be the same. So you've actually changed the interatomic interactions if you do that. This way, the interactions are identical to the original model. The other things are just removed, and we've now put these restraints on the boundary. So you can check that your new system is in fact smaller. In this case, we load it, and that's all we have. We just have this top of the chaperonin in our system. We have 8,928 atoms, so we've reduced the system size in this case by a factor of 6. Although obviously this truncation is not, there's no scientific explanation for why this selection was made other than for demonstrative purposes. But for large systems like a viral capsid, you could imagine that if you have 1,600 proteins, you might want to only simulate 30 of them. So your atom selection could have actually been chains 1 through 30, and then you pull out those 30 chains instead. So we have our truncated system. And at this point, it's the same as any other structure-based model that we would want to run. We have to call GrumpyPee to make our TPR file. I've provided this MDP file in the workshop directory for you to download. It just has recommended values for when you are running the all-atom model. And the only reason it says with restraints is because we are not removing the center of mass velocity. And the reason for that is because we've imposed spatial restraints. So if the system is not invariant to translation, the potential energy is not invariant to translation, you do not want to remove the center of mass velocity. Otherwise, you start having center mass velocity subtractions competing against the interactions in your system. Other than that, this is exactly the same file you would want to use for any other all-atom structure-based model. So you give it with your new grow file, your new topology file, and then you can give it a run. Okay, and it processes pretty quickly. It just takes a second to go through this GrumpyPee step. This GrumpyPee step can actually take a very long time for the large systems. So if you're looking at the ribosome or, again, like a viral capsid, GrumpyPee could take an hour or longer just to produce your TPR file. So don't be concerned necessarily if GrumpyPee is taking a long time and you're simulating hundreds of thousands or millions of atoms. And then we will run our simulation, and I'll explain what this no DD check flag is in a little bit. So in this case, it's just a 10,000 step simulation, but we're now simulating this subset of our system rather than having to simulate the entire chaperonin. So if you're looking at the speed, this is going about as quickly as our C alpha model was yesterday. And that makes sense because the C alpha model was 8,000 C alpha beads. We've now reduced the system size here to about 8,000 all atom beads. Okay, so we'll give it a few seconds, and I'll give everybody a minute to catch up. And I'll load it and visualize it. So if everything went well, you'll have a trajectory that looks something like this, of course. Again, this is too short to be at all meaningful, but the idea can be useful in a lot of other instances. So you could presumably be looking at chaperonin on your desktop instead of having to submit it to a cluster, right? Any questions so far? So it's a pretty straightforward idea, right? We've just tried to make these tools available because this is something we think a lot of people may like to do in the future. As we keep moving to larger and larger systems, the questions just naturally will go towards larger systems. So this is something that could be valuable, and we would like to make it easy for everybody. So we make these tools available. Okay. So that would be an example of how you would set up your truncated systems. Now, the example I gave before of the fluctuation matching, at this point, it really comes down to literally just running the simulation, calling GROMACS RMSF. It will give you your RMSF values, calculating the ratios, and changing the restraints in your top topology file. If you would like to do that, I can send you some scripts. However, they're only like 4 lines long. They're very short scripts because there's not that much beyond. Once you've set up the model, that's sort of the more challenging part. No. Smog Extract only pulls out the force field. The MDP file defines the systems, the simulation settings like temperature and number of time steps. So it doesn't affect that at all. It's just how you define your potential energy is being redefined. Any other questions? Okay. So we'll spend a few more minutes. We're not going to go the full hour and a half, which I didn't think we would. Some tips on performance considerations. Again, as you're moving towards these larger systems, parallel computing is becoming more and more accessible. It's good to have a little bit of an introduction so that you are not wasting time. Right? I found that a lot of students, when they start running these larger systems, I say, oh, is it performing well? And they say, well, yeah, it's running. And it's like, okay, that's great. You're using electricity. That's all you're telling me, right? You're not telling me anything about the performance. And they don't even know how to justify the statement of, is it performing well or not? And so it's just a little bit off of people's radar, especially if you're someone who uses simplified models, because historically we've never had to use more than a couple of cores. Pretty much everything you want to look at, a C-alpha CI2 simulation, you run on 1 core and you get all these folding events in an afternoon. So why would you ever worry about load management of multiple cores? Well, as I said, in these cases for the Chaperonin, you could simulate it on 100 cores. Even the subset could run on, say, 16 or 32 cores. And so there are a few considerations that you should keep in mind so that you're not reserving all these resources and not actually using them. Right? And also, if you're a student, you would like to graduate sooner. So ideally, you would like your simulations to run faster, and you can finish up your projects. So we'll discuss a couple of considerations, and these are completely transferable to any simulation technique that you may be using. So the first thing is, what does scaling mean? So a measure of strong scaling is that if you increase the number of cores by factor n, you will decrease the runtime by a factor of 1 over n. So that is, the time taken on 1 core would be equal to, you could say, the time on n cores times n, or you could bring the divide it by the time on n cores. So this would be ideal. You increase the number of cores, and you get perfect speed up based on that. So you take 1 hour on 1 core, you take 6 minutes on 10, right? That would be nice. And the software packages that are designed to be parallel ideally will run that way. But there's absolutely no guarantee they're going to. So just saying, I started my simulation, I'm running 100 cores, that's great. You could be getting the performance of 5 if you don't check, right? It's still a lot faster than 1, but you're not getting 100 times speed up, and you're actually having 95 cores doing nothing, right? So unless you check, you won't know. So what you have to do is you have to take a calculation, run it on 1 core, then 2, 4, 8, 6, and just keep increasing the number of cores that you're using, and ask, what is that speed up? What is this ratio? And green here would be perfect scaling. Okay, it's perfectly dependent on the number of cores that you're using. In this case, I'm showing a eukaryotic ribosome with 200,000 atoms, or a lattice of a protein. So we actually took the lattice as studied in crystallography and just constructed the lattice and simulated it for fun, essentially. And then we repeated simulations of that system on large numbers of cores. We went all the way out to 4,000 cores for a single calculation, and this was still with a structure-based model using an unmodified version of GROMACS. So we can't take responsibility for the scaling. That's completely the GROMACS guys that have done this. But we can at least say that we are good users and we make sure that it scales well and we're not wasting resources. So as you see, if it's perfect scaling is green, in this very large system, the red line actually stays pretty close to green all the way up to that 2,000 to 4,000 core range. So anywhere less than 1,000 cores, we're getting almost perfect scaling of that system. The smaller system, say a ribosome, of course it starts tapering off much sooner. It's a much smaller system. You can't go to an arbitrary number of cores. You are limited by the size of your system because you're distributing the workload to the cores. If you only have 100,000 atoms, you can't imagine scaling to 1,000,000 cores because you'd have 10 cores working on one atom. And that's a little, maybe there's some really elaborate way to do that, but I'm not aware of it. The only place I know that's even close is D. Shaw, where they're hitting the limit of 1 core per atom in their machine. It's just sort of hard to imagine how fast that is. So you're never going to be able to get 1 core per atom on a normal machine. With these models, it will be somewhere in the order of maybe 200 to 300 atoms per core is sort of where we see things tapering out. And in these two cases, it kept getting faster and faster because we just couldn't go to enough cores. Had we gone out to 10,000 cores, 50,000 cores, what eventually would happen is there'd be a rollover and the speed would start decreasing. So you could be running on more cores and actually be waiting longer because the code can't handle it, the system can't handle it. Okay. So you have to check these things. And when you do this, there are a few considerations, and I'm just highlighting the considerations with structure-based models with GROMACS of what we look out for. And that would be, what is the level of parallelization that you're using? Are you using MPI? Are you using OpenMP? In the case of GROMACS 5, it uses both. And there are a lot of options as to how to balance those two. And then you also have domain decomposition, which I'll explain in a second. So you need to be aware of these factors. Now, what is the difference between MPI and OpenMP? Well, this is just some schematic of some amount of work that needs to be done. And you take that work and you can distribute it to 4 different processors. These would be MPI processes. So you can say each of these processes has its own memory, so it can't access the memory of the other cores. They actually work completely independently. They can work on their own instructions. They can be completely autonomous for a period of time. They do their work and then send the information back. That would be the MPI model of workload. Well, on top of having all of these processes, MPI processes, you can also then break that amount of work down further using OpenMP parallelization. So then you launch multiple threads, and in this case it's showing 4 threads are going to be working, or I guess they only label 3, but they show 4 arrows. So it's showing 3 threads distributing this load. And in the OpenMP model, it's shared memory. So all of these threads can access all of the memory associated with process 0. Now from a user standpoint, that detail is not terribly important, right? The GROMACS team has taken care of this. It does all of this parallelization where you can just tell it how many MPI processes would you like to start, how many OpenMP threads would you like to launch per MPI process, and then you say go, and the code runs. I'm assuming you haven't done something silly that it throws an error at you. So when you're doing this, you can typically use you can take the product of the number of OpenMP threads times the number of MPI processes, and you typically don't want that number to exceed the number of cores on your machine. If you launch more threads than you have physical cores, you don't spontaneously tell the computer it can now do more work, right? You're just trying to schedule more work. So if you were to launch far too many threads and processes for the number of cores available, that could be something that could severely slow down your performance. So typically keep these numbers about the same, although it's worth trying to go past the number of cores because some architectures can actually give you some speed up. The next thing to consider is domain decomposition. And what domain decomposition is when you have your MPI processes, each process has a set of atoms that it's working on for the next number of time steps. And you need to tell GROMACS how should you divide your system up spatially and distribute it across all of those processes. So the way you do it is when you call md_run, you give -dd, and you just give 3 integers. And this is saying how many cells are there in the x direction, y direction, and z direction. So if you had 4 MPI ranks, you could say -dd 411, and it would have 4 cells along x, 1 along y, 1 along z. You could also do 2, 2, 1, or 1, 2, 2. And which one performs better depends on the system that you're simulating. Okay, you can't say up front that one's going to be best. GROMACS, if you don't give this, will make its best guess. There's no guarantee that the best guess will actually be the best. It's just, that's, if it looks at your system, it thinks if you divide it this way, it will work well. And it does a reasonably good job. But still, reasonably good means that you could still maybe get 20% better performance. And if you integrate that over a PhD, that's a year, right? So just put that in perspective for the students. You can wait an extra year because you didn't check, right? You just trusted that the software knew what it was doing. And I've given this lecture to my students many times and asked them if they wanted to wait another year for the calculations to finish. And then they all become benchmarking experts overnight, right? So what do you want to do? You want to prepare a short simulation. We typically use about 100,000 time steps for the structure-based models because there's an initial overhead to get the simulation going. There's a period at the beginning where it starts to balance the load, and it's really not good performance for the first few hundred steps typically. But if you could let it go for about 100,000 steps, it tends to balance things out, and you can get a pretty good measure of how fast the calculation was with those settings. Typically, we like to make sure our jobs run for at least 10 minutes. That's not a strict rule, but we don't want to do something that's so short that all of the time is spent in initialization, because then you don't actually get a measure of parallel performance. And then all of these options that I was telling you about, you need to vary them and repeat the calculation. Okay, so change how you do domain decomposition, change your OpenMP versus MPI, thread count, and there's really no way around it besides trying all combinations. And if you're using more cores, you have more combinations, but you're also using bigger resources, so you should probably take the time to make sure you're using them effectively, right? So you repeat this for 1, 2, 4, 8. And what I was showing you in the plots before were just the highest performing settings. It wasn't that it just naturally perfectly scaled out to 1,000 cores. At 500 cores, there could actually be very bad performance if the wrong settings were chosen. So these are the key considerations you should look for. And even if you're doing things that are only like 10 or 20 cores, you can still get a 20, 30% improvement of performance, so might as well spend the afternoon and do these types of checks. And that's all I have for today. We're always available. Send us emails if you have questions on these types of things. But hopefully that will get you started if you would like to start looking at larger systems, so that you're not not waiting too long. So if there are any questions, I'm happy to field them. Mm-hmm. 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 What do you mean by user-friendly output, and what do you want to write out exactly? So you're talking about at the VMD stage, or? Mm-hmm. Oh, just from a trajectory, you mean? That's a little vague because it does a lot. So if you wanted to get the coordinates, like we wrote out the indices, you can write out the coordinates. That object, that variable top, is actually the. Yep. So let's see. So it'd be something like. So you have something like name. Oh, this is the truncated system, but still, right there's all your C alpha atoms, right? Well, the coordinate file is ASCII formatted, so you could just use the coordinate file if you wanted to extract them. Original. Oh, the GRO file is the new coordinate file, or the original PDB file are both ASCII. You can just open them and pull the lines that you want. If you wanted to do some complex manipulation to pull out specific atoms, then and then save it that way, you have your representation. You can then just say, let's see, oops. You select it and then say save coordinates, and then you can pick your selection and then save it to a PDB format if you want. You could also, there's a lot of other outputs. I think XYZ might be in here. Yeah, you could pick XYZ format, just the coordinates of the atoms. And nope, this is just the example. So it's basically whatever you can come up with, right? So you could say C alpha and y greater than 50. So there we just cut out part of them. If you want multiple, it'd be like P, CA, CB. That'd be C alphas and C betas. You can even do things like not in the search. So the inverse. You could look at, what this would be not C alpha. So everything except for the C alpha, you can invert the search. You can also say things like same residue as. So you make a selection and you keep the entire residue of any atom that is in your initial selection. You can say within, and you can pull things within a distance of a particular atom or a particular group. If there are particular things you're like, I mean, we could talk for a whole day about VMD selections. So if you're going through and you're trying to do something, just shoot me an email. I can give you tips on how to do them, because there's just sort of this endless list. If to give you an idea, in this selection window here, you can actually click and pick what you would like to select. Like, what are the definitions? So you can, serial, index, backbone type, acidic. So this is just a guide for all the types of selections that you could make. So it's quite powerful. Don't underestimate VMD. It's got a lot in it, but it takes a little while to get used to. Right. No, so we've just prepared a truncated system. You would still have to do the iterative fluctuation matching steps. So when I say calculate the mean squared fluctuations, that means run a simulation long enough that the MSF values converge. And that's typically several million time steps at least. So what you do is you perform the simulation, then you can use one of the GROMACS tools to pull out the MSF values, and then you compare those to the target. And then there's some lines in the topology file that, so we didn't go, well, we did go a little bit over what's in the topology file, your atom types and molecule type and so on, but there's a new field here, position restraints. And this extract tool automatically generates this part of the new topology file. So if you would have to calculate your fluctuations, compare them, and then just manually rescale those three values. This is the x direction, y direction, z direction, one by one. I mean, we're happy to share our scripts if you'd like to use them as a guide, but in the end, it's actually only about 20 lines because it's a couple of awk commands, a paste, and a divide. Well, the way these are chosen is anything that had an interaction removed when you truncate it. Drain. if you give the dash restraints option of Smog Extract, it figures out exactly which atoms had interactions removed, and that's what it's listing here. Atom 1, 10, 1009, 16, these were all atoms that had, in the new numbering, these were the atoms that had interactions removed. You could change that rule. You could say it has to be something within 4 angstroms of the boundary if you want it to. In that case, what you would do is you would not tell the tool to automatically generate the restraints. You could just use, say, a VMD selection to figure out which atoms are in that shell, and then you make your own list of atom. This just means harmonic, and then put in some restraint values. So it's not dependent on how you select these atoms. We just, by default, take anything that was perturbed in the model is a candidate for correction. Right? But yeah, you can definitely get. Early on, I was playing around and I just froze the boundary in these systems, and I can't remember the results because they didn't make any sense. Essentially, like the barriers looked very different from what we ended up getting when we allowed the boundaries to move in a reasonable fashion. So you can get almost pretty much meaningless results if you're not careful with how you deal with the boundaries in these cases. Some people do free energy calculations where they put in restraints on the boundaries, but they're not considering any sort of large fluctuations anyway. It's more of a, what effect does this hydrogen have? In which case maybe the boundary effects don't have as big of a role as in our cases where we have a big molecule going through a corridor, and that corridor has to open up to let the molecule pass by, right? But it would still make me a little nervous if I were just putting in strong restraints on the boundaries for everything. Did you have another question? Yes. So let's see. So you can take, yeah, we could talk a whole day about rendering as well, because clearly those movies I was showing you were not trivial things. But you go down to render, and then there's a whole selection of render tools. Yeah, I'm happy to sit down and show you what we do. It's a multi-step process to make. Right. Yeah, we use Tachyon with ambient occlusion, but we do that afterwards. So we render the data files, and then we render them on a cluster. We actually use like thousands of cores just to render the movies. But they're all right there. And you could just take really quick snapshots as well if you wanted to, but they're not going to be that pretty. Right? They're just going to look like what you see on the screen. Any other questions? Okay, well, for all of these models, don't hesitate to contact us if you have questions. We have, on the website, there's an email help list for the other contributors to the tools. There's also a user list that you can email and get help from a variety of people around the world who use these models and have tips. So thanks for your attention, and enjoy your weekend. You're released.